tenses via Chow variety. Mateusz.
Thank you very much. Yes, so there will be two parts of my talks, and it's like from matroids, which really means we have to start somewhere. And I don't think that many people here might be familiar with combinatorics and matroids, so I will take this opportunity to torture you. But at the same time, please feel free to ask questions at any point. And this first part will be not at all about tensors. Actually, it is quite possible that the word tensor only appears in the title. Between my talks, Matej will be giving a talk, and I hope he will manage to convince you that I am not completely crazy and this is going somewhere. So please hold on with me. And the talk is about matroids. And another strange decision I made is that I decided not to define a matroid for you, but instead, I would like everyone to know what is a representation of a matroid. So a representation of a matroid is nothing else than a linear subspace of your field to the n. So I will fix the field to be complex numbers. That's not so important. But it's really important that this is not an n-dimensional vector space. It's really the field to n. And the difference is that the theory of representations of matroids, it's very much about how this linear space is situated with respect to the coordinate subspaces of your k to the n or c to the n. So if you just take a linear subspace of some vector space, you cannot ask what's the matroid and so on. You can only do it when you have a basis of the bigger vector space. So instead of giving you a precise definition of a matroid, let me give you some intuition. You have a finite set, and you want to collect, so you want to declare certain subsets to be independent. Now, maybe you take this subset, this subset. So of course there are some axioms that would allow you to call your family of sets independent. For example, if you have a set, it's quite reasonable to assume that any of its subset is also independent. And it turns out that a very important axiom is that if you have one independent set of smaller cardinality than another independent set, then you can find an element in the bigger independent set and adjoin it to the smaller independent set and still get an independent set. Yeah, I think it's quite intuitive, but it's also maybe the only axiom that defines matroids, because the other two is exactly this thing that a subset of an independent set should be independent, and maybe also the empty set should be independent. Okay? So something very easy, but when I told you that I take a linear subspace of Cn, it does not seem that I have a collection of some points and some of them are linearly independent. So what's the relation? The relation is as follows. Whenever you have a linear subspace of C to the n, you can form a quotient vector space, C to the n divided by L, and this vector space comes with n distinguished points, the classes of the basis vectors. So if you would like to know what's your set that I have been talking about, well, these are just the classes of the basis vector in this quotient space. And what does it mean for them to be independent? Well, it means that they are linearly independent in this quotient space. Yes? No, I don't assume. So it could be that that the class of EI is 0 in your vector space, and then even a one-element set just containing the class of EI will not be independent. It could happen. And in matroid theory, people regard such situations. And notice that this language is essentially the same. If you give me n points in some vector space W, I can always find a linear map from Cn to W that simply maps a basis vector to the given point, the ith basis vector to the ith point, and I can declare L to be the kernel. And so it really doesn't matter if I talk about finite subsets of points in a vector space or linear subspaces of C to the n. Okay, so why I didn't write just one definition of a matroid? So the problem is that matroids are very well known for having many equivalent cryptomorphic definitions. So what does it mean? It means that you can find proofs in matroid theory, and every proof will take a different definition of a matroid, completely different, and it's, I would say, often highly non-trivial exercise to prove that the definitions are indeed equivalent. If you would like to see many definitions and their equivalences, I will advise you to talk to Michał, who likes to go between various definitions of a matroid. So I fixed this one, yeah? A linear subspace of C to the n. And where are we going? In last years, there have been a few breakthroughs in the matroid theory by looking at them from the geometric perspective. So it means that you want to associate to a matroid something like a variety, or maybe even a variety, and from the properties of that variety, read off something about your matroid. And this was particularly powerful in the work of Juni Ha, who later got a Fields Medal for, among others, for those ideas, where exactly one starts with this, a linear subspace of C to the n. But of course, a linear subspace of C to the n is too simple of a geometric object to get some non-trivial combinatorial information. You need to build a more interesting variety. And let me also say that this could be an easy exercise for people here, that the way it was first applied was to graph theory. And if you have any graph, so vertices and edges between them, there is an associated matroid known as the graphic matroid, where your underlying set is simply the set of edges, and you declare a subset to be independent if it does not contain a cycle. And the exercise is to show that whatever graph I would draw for you, you can cook up points in a vector space, 1 point for every edge, such that the points are linearly dependent if and only if the corresponding edges contain a cycle. Okay? And then you can associate a geometric object to such a matroid, and you can read off information about graph from that geometric object. Okay, so let's try to be slightly more precise about what kind of geometric object and what kind of information. We have to remember how our linear space is positioned with respect to coordinates. And this is something that geometers usually don't like. They don't like to put in coordinates. So the idea to remember that this is not just a projective space over n-dimensional vector space is to use something that is known as a Cremona transformation. So it takes a point in a projective space, which is just like a point in the non-zero point in the vector space up to scaling, and you invert all of the coordinates. And inverting all of the coordinates is not really different than taking the product of all but one coordinate. Yeah? This is a very old map. It's a rational map. What does it mean it's a rational map? Notice that I didn't write here an arrow, because if one of those coordinates, for example, is 0, this first expression does not make sense. Actually, if one of those coordinates is 0, the other expression would still make sense. But if two of them, for example, x1 and x2 are 0, then this map would not be defined. Every single product would contain at least one zero, and here we would get the class of 0, which is not a class of a point in the projective space. Okay? So we will have a linear subspace in the domain, and somehow instead of remembering the coordinates, we try to encode it via this rational Cremona transformation. And here we will try to make a first step towards tensors, although it will be not visible yet. We should try to think about the C to the n as diagonal n by n matrices. And if we think about it as diagonal n by n matrices, then you can think that the Cremona map is simply inversion of matrices. Okay? So, or you can also say that you take all n minus 1 by n minus 1 minors of your diagonal matrix. Yeah? So here it would be more like inversion. Here it would be more like taking minors. But we know that, well, inverse of a matrix differs from a minor matrix just by scaling by the determinant. So in the projective space, it's the same map. Okay. So notice that this map completely has forgotten the representation of a matroid. There is no subspace L here. So its responsibility is more to remember that there are coordinates. But now PL comes back into the game, and we can restrict our map to P to the L. So you take a point in a linear space, and you invert all of its coordinates. You take another point, and you try to remember all such pairs. So you remember here a point from P to the L and its inverses. Okay? So what you look at is the graph of a map, of a restriction of the Cremona transformation to the projectivization of the linear space L. Okay? And that's one of the varieties you are very much interested in. Okay? That's the geometric object. It lives in a product of two projective spaces, not just in one projective space, and it remembers all pairs. Then if you want a variety, you have to close it, but most of the points are just a point from your L and inverses of its coordinates. Okay? So what can you do if you have a variety in a projective space? Well, you can ask what is its dimension. That's usually the first question. Here the dimension of the variety I have is very easy. It's just the dimension of P to the L, because essentially for every point of the projectivization of L, you remember its inverse, and Zariski closure will not change the dimension. But if you have a variety in a projective space, there is one more important invariant that people ask often about, apart from the dimension. Anyone can tell me what could be the other invariant of a variety? Yes? The degree. And there are a few equivalent definitions of the degree. Again, you know, just like combinatories, they prove that there are equivalent definitions of a matroid. People in algebra prove there are equivalent definitions of the degree. One of them, if you have a variety in a projective space, you just intersect it with hyperplanes, different hyperplanes, until you get points, and you count how many points you get. But now, our variety is not in a projective space. It's in a product of two projective spaces. So it does not make sense to say, oh, let's take a hyperplane. The only thing we can do is like we can take a hyperplane in one of them times the whole second space. And let me call it H1. Or we can take the whole first space and a hyperplane in the second projective space. Let me call it H2. So now when I have a variety, I can intersect it with H1, 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 and count how many points I get. That's one number. But I could also intersect it with H1, 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 H1 until I have a curve, something of dimension 1, and then I can intersect it with H2. And then count the numbers, the points. And I get a second number that usually is different from the first one. Or I can just intersect, for example, with H2, 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 H2. So I don't get just one number as the degree. What I get is a sequence of numbers, dimension of your variety plus one many, yeah, where I only determine how many hyperplanes of type 1 I take and how many hyperplanes of type 2 I take. And this is called the bi-degree, okay? And it turns out that the bi-degree of this very easy variety encodes a classical combinatorial invariant, namely values of the absolute values of the coefficients of the reduced characteristic or chromatic polynomial of the matroid. Many words, right? I mean, but let me just give you some hints what those words mean. So I said that important class of matroids are those that come from graphs. Okay? Now, if you have graph, since you are a child and mathematicians for a few hundred years, you may want to color it, right? So you can, and we will be coloring vertices. So you can color this blue or color number 1, this color number 2, this color number 1. And the coloring is called proper if you don't have two vertices of the same color joined by an edge. Okay? So if I give you k colors, you can ask how many ways are there to color your graph? How many proper colorings are there? So if I give you one color, the answer is usually 0, right? You cannot color a graph if it has even one edge with one color. But, well, as there are more and more colors, you will get more and more proper colorings. And it turns out that this function is a polynomial. From the very beginning, this is a polynomial, chromatic polynomial. Proof has one line. It's induction on the number of edges. And because 1 goes to 0, this polynomial needs to have a root at 1. So you define the reduced chromatic polynomial as the chromatic polynomial divided by x minus 1. Okay? And how could you compute such a chromatic polynomial? Well, if you think about this induction, how to prove that it's a polynomial, you will see that it's actually a recursive formula. And you can use such recursive formulas to prove actually that the coefficients of this reduced chromatic polynomial is the bi-degree of the variety I have given you. Okay? And this is exactly how Juni proved, I think it was like 100 years old open conjecture on the log concavity of the coefficients of this reduced chromatic polynomial. Namely, in algebraic geometry, we have something called Hodge index theorem. And Hodge index theorem is a little bit like Nullstellensatz. Depending which mathematician, algebraic geometer you ask, they will give you a different version. But going from one version to another is not very difficult. Yeah? So maybe proving one of the versions is hard, but once you have one version, then going to the others is easier. So I give you Hodge index theorem in the version by Juniha, that if you take any irreducible variety in a product of projective spaces, the bi-degree is a log concave sequence. And that's the end of the proof. Yeah? The coefficients of the polynomial, they are encoded by the bi-degree. Hodge index theorem tells you it's log concave. Okay? Yeah. I really love this proof because, you know, once you know the steps, it's like, yeah, you can do it. But getting the steps, I mean, it was considered to be very, very hard. Okay, let's continue. Now, not every matroid comes from a graph. And it's not even true that every matroid comes from such a linear subspace of a vector space. And then there are more general conjectures where they seemed much harder to be approached because You didn't have even this linear space to start from, so how do you build an associated geometric object? Second thing is, notice that if you restrict the graph, you could first ask what is the variety if you take the whole space. Yeah, if you just invert every point in PC to the n and you remember this, then you get some subvariety of the product of two projective spaces. And it might seem that, oh, this has to be some beautiful, well-known variety, but actually it's not so nice. It's quite singular. And if you want to take a subvariety of something singular and then do intersection theory with it, this is usually not the setting that algebraic geometers are most happy with. We prefer smooth projective varieties. So this will be our second motivation. One, we want to go to other matroids. We want to have a smooth smooth variety, and maybe those other matroids, they will not be subvarieties, but maybe they will be more complicated objects that we will introduce next, like some elements of the cohomology ring. Okay, so before I give you a formal definition of the permutahedral variety, I want you to have an intuition what it is. It will be something, yeah, so maybe let me write it on the board. So we have our Pn, we have our Cremona, which is rational, it inverts coordinates, and we have the graph of the Cremona, which just lives in a product. Okay, so these are like pairs, a point and its inverses. So the permutahedral variety will live above this. And it will be smooth, and there will be open sets here, 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 and here, which can be just identified. So in algebraic geometry, we call it birational. So notice that whatever this variety is, it needs to come with a map to one Pn and the second Pn. Okay? But maybe we need more projective spaces. Now, graphs we know from primary school, right? We remember x and f of x. And in algebraic geometry, we use more fancy words for graphs. We say that it's a blow-up. Yeah? We would say that we are blowing up Pn in whatever the zero locus of the polynomials defined by this map are. But for technical reasons, we prefer to blow up smooth subvarieties. So I told you that here the problem is that this map is not defined when we have two zeros. So these are coordinate subspaces of codimension 2. But this is singular, yeah, because they intersect, and you get coordinate subspaces of codimension 3. So the idea is, oh, maybe I will first blow up those coordinate subspaces of codimension 3, but this is still singular, because they intersect along coordinate subspaces of codimension 4. Oh, so maybe first I should blow up that, and this ends at some point. Yeah, you will get coordinate lines, or if you think projectively, you will get points, and the points will not intersect. And that's the idea behind the permutahedral variety. So instead of taking the graph, I will take the image. That's why I first remember. Yeah, so this PC to the n is exactly the same as this PC to the n. So I take a point and just remember it. Yeah? So instead of talking about graph, I could just build a bigger map from Pn to Pn times Pn, where first I copy identity and then use a function. Okay? Then, well, I told you I have to blow up points. But so all coordinates are 0 apart from 1. So what are the polynomials that vanish on such a collection of points? Well, these are products of two distinct coordinates. Okay, so this is responsible for the blow-up of points, and so on and so on. The last thing is what we had previously. So I take n minus 1 different coordinates and I take their product. And the permutahedral variety, by definition, is the image, the closure of the image of the left-hand side into the right-hand side. And notice that it does come with the two projections I promised you, because you can project to the first factor or you can project to the last factor. And it's not defined everywhere, because if you have many zeros, then of course sometimes you will get, this does not have to be well defined. And if we want to go towards tensors, we should think that we are not blowing up points here. We are blowing rank 1 matrices, diagonal matrices. And these are not products of two distinct variables. These are 2 by 2 minors. Okay? And then you have to blow up not lines, but rank 3 matrices, and you will take 4 by 4 minors, and so on and so on. Okay? So I hope that you can maybe relate that the closure of the image of this map is something like blowing up iteratively, dimension by dimension, I-dimensional coordinate subspaces. And the way to think about it is that you are blowing up rank 1 diagonal matrices, then rank 2 diagonal matrices, then rank 3 diagonal matrices, and so on and so on. Okay? Everyone happy with the permutahedral variety? Are there people here interested in toric geometry? Or not really? Is there anyone interested in toric geometry? 1 person, 2 people? So for people who like toric geometry, this is a toric variety, and you can try to think what's the polytope, and you will arrive at the polytope known as the permutahedron, which is the convex hull of all permutations from 0 to n minus 1 of points. Okay. So we have this permutahedron that maps to our left projective space. It also maps to right, but in particular it maps to left. And we said that the representation of a matroid is inside this Pn. So it seems that an important variety is something like a pre-image. But, well, taking formally pre-image is not the best idea. What you should actually do is you should take the open sets on which these two varieties are isomorphic and see how this PL intersects this open set and take the pre-image and close. This goes under the name strict transform in algebraic geometry. Yeah, so you know, this permutahedron, notice that this map, when your coordinates are non-zero, is an isomorphism, right? If all of the coordinates are non-zero, then the point uniquely determines right-hand side, and right-hand side uniquely determines the point. So this set and this set have the same open set where the coordinates are non-zero. So you look at your points in P to the L where the coordinates are non-zero, and you close it in the permutahedron. This goes under the name wonderful model of, let's say, a matroid or associated to a representation. And this is a smooth variety. You could have also constructed it by taking your PL and looking what are there, rank 1, rank 2, rank 3 matrices, again thinking as the ambient spaces diagonal matrices, and blowing that up. This would give you the same wonderful model. And I would say that in this modern matroid theory, this was very powerful to understand how this variety sits inside this permutahedron. Okay? So what does it mean, how it sits inside? I mean, what are you talking about? Let me maybe go back here. Notice that now I have many hyperplanes. I not only have H1, which was a hyperplane here times everything, or H2, which was a hyperplane here. Now maybe I should have called it Hn-1, which was a hyperplane here times everything. I have also a hyperplane in every single of those projective spaces times everything else. So now when I will talk about degree, is not only a sequence, it's like a whole simplex filled with numbers. And this we would call, let's say, a cohomology class of the wonderful model inside the permutahedral variety. Oh, not even, this would be even less information than that. Okay. But you would get a lot of interesting numbers, right? Yes. And some of those numbers, namely if we would only intersect with hyperplanes here and here, they were the main step in the solution of this log-standing log concavity problem on coefficients of the chromatic polynomial. I realized I talk about log concavity. Maybe I should have said what it means. I mean, a sequence is log concave. If you take logarithms of numbers, then it's concave. Okay? That's log concavity. Okay. So now, fun ends. Now we have to do some work. So I want to tell you what's the idea behind the Chow ring. So to every variety, we associate some ring. And in all examples that I will be using, if you know cohomology, this will be the cohomology ring. But if you don't know cohomology, let me tell you what are the elements of this ring. Well, the basic element should be a subvariety. But you have to be able to add subvarieties. So this will be formal combinations of subvarieties. Something like this line plus this circle minus 3 times this point. This would be a representative of an element of the Chow ring. But there are so many subvarieties, right, uncountably many, that this would be a too big ring. So you put equivalence classes on your subvarieties. Namely, if you take any I+1 dimensional variety and map it to P1, you want to say that any two fibers are the same. So for example, any hyperplane in a projective space will give just the same element in the Chow ring. Yes, please. No? Ah, okay. Okay. Addition is formal, and multiplication under mild assumption in this ring corresponds to intersection. Okay? So maybe now it's time for an example. If you just take the projective space, it turns out that there is just one generator. It's like a polynomial ring in the class of a hyperplane. But if you intersect n+1 hyperplanes, you get an empty set, so this should correspond to 0 in your ring. So the Chow ring of a projective space is ZH divided by H n+1. And if you take an irreducible variety X, you can ask, I told you that a class should give you an element here. Well, it's just H to codimension of X, and the coefficient is the degree of X. Yeah? So some hypersurface of degree 2, you will not distinguish it from two hyperplanes. Okay? And addition, as I said, is formal, O. And well, multiplication is, of course, as if it was a polynomial ring.
Under which conditions is the Chow ring equal to the homology ring?
So the condition that is very nice to use is affine stratification. So you can subdivide your big variety into affine spaces, like you can do for a projective space. Yeah, there is a big affine subspace of a projective space, and the complement is a projective space, but you can continue. There is a smaller affine subspace in this complement, and so on. And then if you are blowing up in such things and so on, this is preserved. So, in all of the constructions I will be doing, they will be the same. One has to be slightly careful about grading, because usually cohomology rings have doubled grading, because people count real codimension instead of complex one, but that's minor. Okay, we continue. So maybe before we continue, and the questions like, do you have a feeling what the Chow ring should be? It's a very small ring, right? It's not like infinite dimensional and so on. It's a graded ring. And, well, for projective space, it's very easy. For permutahedron, it's more or less understood. I mean, you can write it as generators and relations. In general, it's not so easy to understand. It does not have to be generated in degree 1, but I don't know, like 50 geniuses in last 150 years spent their lives in order to have a good understanding of sufficiently many Chow rings. So I would say it's a pretty well understood subject. Okay, so this is the story how it looked like, I would say, about 10 years ago. But in last 10 years, new things appeared. And the new thing is that after all, on the first slide, a representation of a matroid was a linear subspace of C to the n. It was not the projectivization of L inside a projective space. It was just a linear subspace in C to the n. So the idea is that maybe I shouldn't projectivize this part. I should rather, so why do we projectivize? Because we like projective varieties, because they are compact. But instead of projectivizing, there is another way how you could make things compact, projective, namely you could compactify. So the idea of compactification of C to the n is to take P1 to the n. So you just take a projective line times a projective line times a projective line. N products of projective lines is not an n-dimensional projective space, it's something else, but it's a pretty easy object. And how do you put C to the n inside here? Well, if you have x1, xn, you map it to 1, x1, that's a point in the first P1, 1, xn, that's a point in the last P1, okay? And this is really an embedding, okay? And we still want to remember that this L had the structure of a vector space. So we would like to say it somehow geometrically, at least that it's a cone. So or at least that it's invariant under scaling. So I can remember it by saying that C star acts on L, right? I mean, T times L is just TL. But this action of C star extends to P1 to the n. Namely, if you give me a point in P1 to the n, I can just act on second coordinates. And this will be the same on L. But now I act on the whole P1 to the n. Okay, very good. So a matroidal Schubert variety is the closure of L in P1 to the n under this embedding. Yet another geometric object associated to a linear representation of a matroid. Okay, but now it doesn't live in a permutahedron, it lives in P1 to the n. So some people raised hands that they like toric geometry. The difference in polytopes is that instead of working with the permutahedron, which is maybe complicated, you just work with a cube, which is easy, yeah? Like cube, like segment times segment times segment, just maybe in higher dimensions. Okay. Now, the loss is that this variety can be singular. So the wonderful model, XL, was smooth. But YL, the matroidal Schubert variety, can be singular, but still it reflects a lot of combinatorial structure of the matroid of L. And I think the first appearance was in a paper by Federico and Adam with a very suggestive title, The Closure of a Linear Space in the Product of Lines. Yeah? The title essentially gives you the definition. But I think at that point, people did not realize how important it is until Juni and Botong proved some old open conjectures using this variety YL in their work, enumeration of points, lines, planes, etc. Okay, so we have two different constructions for matroids. One is XL, one is YL. And they seem not related, right? Once we were projectivizing, once we were just closing in P1 to the n. So to keep you focused, let me tell you that our aim is to go towards tensors, and this will happen. Essentially, everything I said will lift to tensors. But first, let's understand the basic case of matroids. And to relate the two constructions, we need one more definition. And this is another 100-year-old or more even idea, going back to Chow. So I think I have time, so let's play a game. Your aim is to send me a data about a subvariety in a projective space. So X is an irreducible subvariety in a projective space, but you are only allowed to send me one point in some projective space. Okay? So you somehow have to encode the whole variety just in one point. Okay? So let's say that I give you a zero-dimensional irreducible variety in Pn. What would you send me? The point. Okay, very good. That's a good answer. I give you a point, you send me the point. Now, what if it's a hypersurface defined by f? The equation as a point in the space of polynomials, right? Okay, so these are two very good ideas, but they seem different, right? Once you send me the point, once you send me the equation. So is the point an equation of some hypersurface? Is a point an equation of some hypersurface? Of a curve? I mean, if it's a point, let's say, in a free space, is there some hypersurface of which it's an equation?
The point literally is a hyperplane in the dual space.
Yes, right? Points are hyperplanes in the dual projective space. So maybe you didn't send me the point. Maybe you sent me the point, the equation of a hyperplane in the dual projective space. But what's the hyperplane in the dual projective space? It's the locus of all hyperplanes going through the point. So you took all hyperplanes going through the point. Now let's go back to the hypersurface. You send me the equation of a hypersurface, but there was no this, oh, let's take all things going through the points. So maybe you took all points going through the points of your hypersurface, and then you send me the equation of that. So once you breathe in those two examples, I hope that now the general definition will be easy or easier. So this is an idea of Chow. So for a point, we were taking all hyperplanes that meet that point. For a hypersurface, we were taking all points that meet that hypersurface. That was step one. So if we will have a d-dimensional variety, a general n minus d minus 1 projective space will not intersect it. But maybe if I take those that intersect it, maybe that's an important object. The thing is that those projective spaces that intersect X, they don't live anymore in a projective space. Where they live in is the Grassmannian. So the Grassmannian is a variety whose points exactly correspond to projective subspaces of a projective space of a given dimension. Yeah? So to my X, I can associate, if I didn't have this minus 1, then every single one would intersect, and the general one would intersect in degree many points. But because I have this minus 1, I get some proper subset of a Grassmannian. And it turns out that it's a hypersurface of the Grassmannian. It's a codimension 1 subvariety of a Grassmannian, and you can reconstruct X from that hypersurface. Okay? Grassmannians, they like to live in a projective space. In the two examples I gave you, these Grassmannians literally were projective spaces, but normally you have to do the Plucker embedding, so you do get some subvariety of codimension 1 in the Grassmannian, which lives in a bigger projective space. Now, once you put your Grassmannian in the projective space, there is the coordinate ring of the Grassmannian. It's just the polynomial ring of the projective space modulo Plucker relations. Yeah, Plucker relations are quadratic relations that generate the ideal of the Grassmannian. And the ring associated to the Grassmannian is just the polynomial ring on the ambient projective space modulo those Plucker relations. So if I give you an element here, it does not make sense to evaluate it at the point of a Grassmannian, but it does make sense to ask whether it vanishes or not on a point of a Grassmannian. Just like if you have a homogeneous polynomial, you cannot evaluate it on a point of a projective space, but you can ask whether the homogeneous polynomial vanishes or not on this. And the same for, this is a graded ring, and if you take a homogeneous element there, you can ask whether it vanishes on point. And if you have a hypersurface, you can take the ideal of all polynomials that vanish on your hypersurface, and what you get is up to scaling an ideal generated by up to scaling unique generator fx, which is called the Chow form. So you should see here taking the equation of a hypersurface, just when the hypersurface happens to be not of codimension 1. Okay, so this fx is a Chow form, and what is more, the degree of that generator is only governed by the degree of x. So you can send me this generator in the projectivization, oh, I missed the projectivization of the degree x part of this ring. Let's breathe it in. Maybe questions? Yeah.
What's the Plucker embedding?
So, yeah, let's write it. So if you have r-dimensional subspaces of V, there is a natural way to put it in this projective space, where if you have a subspace L, it's generated by V1 up to VR. You send it to V1 wedge V2 wedge VR. So this is how an algebraic geometer would see it. Any other normal person would tell you, take the matrix that spans your subspace and take maximal minors and remember them. Okay? Okay. So now magic happens. Chow was really a genius. So you can do this for subvarieties of fixed degree. If you're in a fixed degree, you land in a fixed projective space. But it turns out that if you just do it for subvarieties, you don't get a closed set. If you take every single irreducible subvariety of degree d, and you take their Chow forms, it's not a closed set in the projective space. But it is if you allow your varieties to be reducible, and additionally, if you assign them multiplicities. So you take one line, and another line with multiplicity 2, and you treat it as something of degree 3. Okay? And the construction is just the same. You take all things that meet it, yeah, but there will be squares. Yeah? So if you have something of degree 2, you will have to square the equation. And such things, such combinations of irreducible subvarieties are called cycles. They were also important in our construction of Chow ring. But here there is no equivalence. In some sense, it's even simple. To any cycle, you associate such a point in a projective space, and this forms a variety known as the Chow variety. Yeah? So when I was introduced, there was Chow quotient, but it was misspoken as a Chow variety. So now you know, oh, what's a Chow variety. And the advantage of a Chow variety is that to define it, you don't have to use the word closure. Every point in a Chow variety really corresponds to some cycle of fixed, equidimensional cycle of fixed dimension and degree in a projective space. And this is a bijection, so points really correspond to cycles. And why is this important? Well, it's important to construct the Chow quotient. So now we have a subvariety of P to the n, and the group acts on it, G. Now, you know, when a group acts on a variety, it's like in Jarek's talk. Maybe there are fixed points, maybe there are huge orbits, but almost all orbits look the same. What do I mean by this? There is an open subset where every orbit will have the same dimension and degree. Okay? So whenever I take an orbit in this U, there is an associated point in the given Chow variety corresponding to it. There is a point corresponding to the closure of the orbit in U. And then the Chow quotient of x divided by g is defined as the closure of the locus of points we get from orbits in U. And you can say, oh, but again, there is this closure, this not nice closure, so how will I know if points are there? But remember, we are still in the Chow variety. Chow variety is closed, so the closure will live there. So points in the Chow quotient will still correspond to G-invariant cycles in X. So what happens is you have a point corresponding to this orbit, you have a point corresponding to this orbit, you have a point corresponding to this orbit, and in the limit, the orbit breaks, maybe into the closure of two orbits, and there will be a point in the Chow quotient not corresponding to this orbit or to this orbit, but to this cycle. So you take the closure of this orbit plus the closure of this orbit. Okay? So the advantage is that points in the Chow quotient have really nice geometric interpretations. Okay. So I think I only have 5 minutes left, and it's time to do some examples that will join the two constructions I have given so far. So wait. Do I still have? Okay, I still have one more slide, so good. I was afraid I have to draw the diagram. Okay, so we have a C star action on P1 to the n. And I already told you that you should imagine this P1 to the n as a cube. It's like a segment times a segment times a segment. Every segment is one P1. And a typical orbit does something like this. It starts here, goes inside, and ends here. But there are special orbits that maybe they start here and go here. Or even more special orbits, like this line is an orbit. Or maybe even a more special orbit, like a fixed point, which is like a vertex. And you can slightly see what happens. If you take an orbit, if you will go with it to a boundary, it will start breaking. Maybe it will break to this, and this would be a point in the Chow quotient. And then you can even specialize it more. So you get like a completely special union of three orbits. This, and this. Okay. So can you see how many those super special ways of going from this vertex to this vertex there are? Yeah. I want to get from this to this. I have to go right and up. And I can only use edges. 3 factorial, yeah? That's a good answer. Yeah? First I have 3 choices, and then I have 2 choices, and then I have to just get there. So permutations, such a path from here to here is actually a permutation. And in this 3-dimensional example, you can even cheat more. You could cut this 3-dimensional thing like here, 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 and here, and you would get a hexagon, and every orbit or a union of orbits in the Chow quotient would correspond to exactly 1 point in this hexagon. And this can give you an intuition. A hexagon is the convex hull of all permutations of 0, 1, 2. It's a 2-dimensional permutahedron. So what happens is that the Chow quotient of P1 to the n is the permutahedral variety. And I was very happy when I discovered that. Of course, only to discover that mathematicians knew it for at least 20 years before me. I think this is in Bernd's Sturmfels, Billera, Annals paper, where they exactly say how Chow quotients of toric varieties look like. And essentially what you have to do, you have to chop your polytope. So you have to cut it, and you have to do Minkowski sum of the pieces. Okay, so in last 2 minutes, I want to join the two constructions we had. So we had P1 to the n, which was a compactification of Cn. And here we had projectivization. We constructed the permutahedron as the blow-up of this Pc to the n. But, sorry. But now I told you that there is a Chow quotient thing here. So this contracting orbits to points here, you can also see it here. This is the Chow quotient by the C-star action. But I also told you that the permutahedron lives inside the product of projective spaces. Okay, before I used to write C to n choose I, but this is the same as wedge I Cn. And P1 to the n is also a projective variety. I told you it's not Pn, but there is a way of embedding P1 to the n in a bigger projective space. Okay, so typically people here, I think they would write just C to 2n, meaning you take, if you think about points in your P1 to the n as AI, BI, you have to remember how many AIs and where you take them, and the others you take BIs. So this would be subsets. But I somehow here grouped the coordinates. This would be the weight decomposition in the algebra, geometric, or representation theory, because I have a C-star action. So my A's are of weight 0, and my B's are of weight 1. So I have n choose I subsets that correspond to weight I. And on this projective space, also my C-star acts, but simply those n choose I coordinates here, they are scaled by t to the I. And then this C-star action is compatible with the C-star action on this P1 to the n. Okay? And you can see that this rational map here also contracts C-star orbits. This, downstairs or upstairs? Product of projective spaces. Yes, sorry. Maybe big O plus is not the best notation. Yeah. So it's not, yeah. I mean, you see, this Chow quotient is about this arrow. But it contracts orbits. So you ask what you should do to do the Chow quotient. You have to do a bigger Veronese and essentially then do the same. No, so I didn't write here that this is the Chow quotient. I just said that if you take an orbit of C star, it will go to a point here. We can discuss it. So these are our steps towards tensors. Thank you.